those at home hear me? If you can hear me, raise up your hands. Otherwise, I do not know. Okay, so it's clear enough, huh? All right, so this is what we are going to do. Let me see if you can do it. Okay, you can put out your hands now. Okay. Now, it's a bit troublesome. Okay, so this is what we are going to do today. Yes, okay. So what we are going to do is on your tutorial 3, and the 4 important things is the probability itself, and this concept called area under the curve, which you, for those doing, if did AMAX before, you should know the area under the curve, okay? And then we talk about conditional probability before we go to contingency table and relative risk. Okay. So number 1 by itself, let me go and get another pen. Okay, so number 1, what is probability of something happening? Probability. What is probability first? Okay, so probability is basically a chance of an event. Okay, or it can be multiple events as well. Okay. But probability, is there a limit? That means is there a maximum number and lower number? Okay, probability itself is bounded by, you can go all the way to 0 and 1. When something is 0% probable, that means it is impossible. When something is 1, it means that it is 100% likely. That means it's always going to happen. Okay. Going to happen. Okay, so which means that, let me just save this. Save. Okay, and I save as 24. Okay, yes. Okay. So what does all this means is, probability must always be at most equals to 1, which means that, okay, oops, empty, how do I get a new sheet? This, okay. So the probability of an event happening plus the probability of an event not happening equals to what? Huh? 1, correct. So probability of an event happening and probability of not event happening equals to 1. Okay.
Equals to 1.
Yeah, equals to 1, all right. Okay. All right, good. So what do you think, let's say if I want to find out, for example, you have 2 dice. Okay. What is the probability of getting maybe a number 8 for 2 dice throw? So how do you get 8 first? So you have, okay, let's start. Can you do 1 and something?
Is it 1/6 times 1/6?
Okay, so you have 2, 6. Any other options? 3, 5, 4, 4. Then there is 5, 3, 6, 2. Okay, so there are 5 possibilities out of what is the total number of possibilities that you have for 2 dice throw. More than that, the number is maximum 12, but it can be from 1, 1, 2, 1, 2, and so on. So it's out of 36, correct? So the probability of getting an 8 is equals to 5 out of 36. Then you convert it to a decimal point. All right. Now, how about if I were to tell you that the probability, let's say Singapore, it rains. For example, it rained 20% of the chance of the time. But also, you know that Singapore on roughly the day and night is equal, right? So the day is about 50% of the time, correct? So if I want to ask you to find out what is the probability of raining in the day, how will you do that? Correct. So you just multiply, and you multiply the probability. Here you get 0.2 times 0.5. So basically 10% chance that it will rain in the day. Okay. So in another words, your Venn diagram, you can draw it this way. You have rain and day. What you're looking at, N is always intersection. Okay. When you have N, okay, another color. When you have N, it's always intersection. Okay. If you have or, then will be a union. Okay, so that's a fundamental rule for things. Okay. So for example, if I were to ask you, what is the probability of day or night? Correct, because you take probability of day plus the probability of night. Okay, so union simply means it is addition. So here you have probability of day is 0.5 plus 0.5 equals to 1. All right. Any problems so far? Okay. So once you are able to do that, then let's look at this thing called area under a curve problem. Okay. Area under a curve is actually not part of your syllabus, but it actually helps you for the next chapter. Okay. So let's say we have 2 dice. Okay. Each die has 6 faces. Then we want to look at what is the probability of every number. Okay. So let's look at this. If I just were to draw a number scale, there are possibly 12 outcomes, right? Do you think first is 2 dice, can you get 1? Cannot. So minimal, you get 2. Okay. So 2, how to get 2? Eh? 1 and 1. Make sense? So you get 1 and 1. Okay. How to get 3? So we do 1 at a time. 1 and 2. Any more? Yeah, 2 and 1. So 2 and 1. So you build up the block. Any more options? All right. So how about 4? Okay. You have 1 and 3. 2 and 2. Any more? Correct. 3 and 1. Any more? No. Okay. So how do you get 5? 1 and 4. Next. 2 and 3. Yep. 3 and 2 first. Then. Correct. 4 and 1. Okay. Any more? No more, right? 6. So how do you get 6? 1 and 5. 2 and 4. 3, 3. 4, 2. And then 5, 1 on top. Okay. To get 7 is 1 and 6. Then 2 and 5. 3 and 4. 3 and 4. 4 and 3, 5 and 2, it's just reverse. And here, 6 and 1. Okay, to get 8. How do you get 1, 7? Huh? 2 and 6, correct. So you end up with 2 and 6. There's no 1, 7. Okay. After that, yep, 3 and 5, 4 and 4. Any more? 5 and 3, and 6 and 2. Okay. 9. 3 and 6. Please, you just reverse it back, right? 3 and 6. Okay, next. 4 and 5. 5 and 4, correct. Then will be 6 and 3. Okay. Then it's get easier already, what? 4, 6, 5, 5, 6, 4, correct. 11, 5, 6. It's just 6, 5, 4, only 6, 5. And finally, you have 12, correct. So here is 6, 6. Okay. So now this in itself is, if you actually, based on what you learn on your distribution polygram or polygon, okay, you will actually draw a line across this, correct? Okay. So basically, we can take the area under this curve as the probability. Make sense? So now, if I want to say that, what is the probability of getting 12? What do I really do? I count one piece out of 36 pieces here, correct? Then I convert into a decimal point. Okay. So the area under a curve is a probability. And I can say that probability, because as we say just now, probability has to be equals to 1 in totality. Okay. So this is very important. Now remember, for those of you who have done A maths, if this line here have a equation, so of my probability equals to a function. How do you find area under a curve? You integrate it, correct? So if this, no, not probability, this is the frequency. If it's equals, let me just rewrite this. Okay. So if the frequency, and basically this is the frequency axis, okay, which means that the probability is actually equals to the integration of your fx. Right? From the line itself to find area under curve is integration. Okay, for those who do not know A maths, you just know that area under a curve can be found by this concept known as integration. That's all. That's all you need to know for the next few lessons. Okay, so this is actually quite important. All right. Okay, where am I now? Here. Okay. Now, since we have that, what is the next thing that we have to do? Let me just go and look at my, now I have a problem. Where do I find myself? What's the next thing I wrote? Conditional probability, yes. Conditional probability. So conditional probability, what do you know by conditional probability? Anyone? Even those at home can answer, because otherwise you'll be answering the homework, the tutorial questions. What do you know by conditional probability? Okay, essentially it is what is the probability of an event happening, okay, given that another event had happened. Okay, so in this way, what we are doing is, if we say that we write this way, A bar, this is not divide, A bar B means that you are looking at what is the probability of A happening given that event B had happened. Okay. And the formula is the probability of event A and event B happened divided by the probability of event B happening. Okay, this is the formula. So this is very important. This is the formula itself. Okay. So let's use this to find out something. Okay. So let's say that, let me just change the color. Light blue. Okay. So for example, we say that probability of rain is, let's say, 1%, 10%. Okay. And we say that the probability of, let's say, John take cab when rain is 60%. Okay. The probability of John take cab without rain is maybe 20%. Okay. And this is the thing that we want to ask. Let's say that you are now in school. Okay. You see that it is raining. It's raining already. And then you want to ask, okay, what is the probability that John is taking a cab? So this is a question you want to ask. You already know that it's raining. What's the probability of taking a cab? Or you can reverse it. What is the probability of, if John is taking a cab, coming to school and it tells you that it's expensive about cab and so on, what's the probability that it's actually raining outside when you're in lecture theatre, you can't see anything? Okay. So let's work out this one at a time. Okay. So how do you actually do this? Number one is draw the tree diagram. Okay. So how do you draw a tree diagram? Okay. Now you have, first, you decide rain or no rain. So the probability of raining is what? 10%, right? 0.1. The probability of not raining, 0.9. Okay. Because these two have to add up to 1. Okay. Then after that, rain, you split up cab, no cab. So rain, what is the probability of taking a cab? 0.6 right here. Okay. So 0.6. Rain and probability of not taking a cab? Correct, 0.4 here. Okay. No rain, John may also take a cab. So if there's no rain, what's the probability of John taking a cab? 0.2. correct? Then here, 0.8. All right. So let's work out the equation. The problem. So let me just take a color first. So the probability of cap when rain. Okay. First, you have to find out the probability of cap and rain. Divide by the probability of rain. Correct? So what's the probability of cap and rain? Okay. Is 0.1 times 0.6. Rain 0.1. Make sense? So in this case, you have 0.6. Okay. So this is the easy part. Now let me just save this first. Okay. So now we just solve this part here. This is equals to 0.6. Okay. So let me erase it. Erase, where's my eraser? Okay, large eraser. So we want to find out the other way, which is this. Okay. For example, John comes into school by cab. What is the probability that it is raining outside? Okay. So now what you have is probability of John getting a so you now have to reverse. This is rain, given that he's already taking a cab, correct? Okay. The numerator is still the same. Rain and cab. But the denominator now is cab. Okay, so how do you work this out? The numerator is still the same because rain and cab and rain is the same, correct? So let me change the color first. So this is still 0.1 times 0.6. How about taking a cab? Now you have to see that there is actually two cab. So the first one is you have to take, because this is 0.1, it's still the same, 0.1 times 0.6. After that, you have to add on to the next one, no rain and cab, 0.9 times 0.2. Okay, so can somebody help me calculate? The calculator. Huh? 1/4, so 0.25. Okay. What you will see is these two numbers are not the same, which means that, very importantly, okay, probability of event A given B happen is not the same as probability of event B given A has happened. This is a very important point. Okay. So with that, you can actually calculate a lot of different things now. So now what we want to go is basically, you already covered your contingency table. So because we have done the practical already, makes your life a lot easier. So just delete the whole thing. Okay. So contingency table, how do we construct? Which is the exposure, which is the outcome? Rho is exposure or rho is the outcome? Okay, so it's correct. So we want to have exposure. The exposure is you have a positive exposure and negative exposure. Then you have the outcome. Okay, so you have positive outcome and negative outcome. Okay, then by nomenclature we call this as A, B, C, and D. Now, out of these A, B, C, and D 4 quadrants, which number should be the largest most of the time? Okay, so usually, almost always, I'll say, almost always, D is the largest. All right. Okay. Now, based on this, we can actually calculate two things first. Okay. We can calculate this thing known as the outcome ratio. Okay. So we can calculate the outcome ratio. Here's the outcome ratio. Outcome probability. Okay. That means what is the probability of what is the probability of a positive outcome given the exposure or not the exposure? So here we have A divided by A plus B. Okay. Here we have C divided by C plus D. So this itself, these two components is what we call as the risk. Okay. Then what you have is the relative risk. So relative risk is the ratio of risk between presence in exposure and not absence in exposure. Make sense? Because it's a ratio, presence in exposure and absence in exposure. Okay. So indirect, you're just taking one divided by the other, which is why relative risk is this. Okay. How much more risk, relative risk is really the measure of how much more risk given exposure, presence or exposure. Okay. For example, you are looking at, let's say, normal situation, how much more risk of having a lung disease when you are 50 years old if you are a heavy smoker versus you are a non-smoker? So how much more chance of happening? That is relative risk. So when relative risk equals to or close to 0, when relative risk is close to 0, what it means is presence of exposure does not increase the prevalence of a positive outcome. Okay. That means whether you smoke or don't smoke, the chances of getting a lung disease at age 50 is the same. Then smoking has no effect. Make sense? How about when relative risk is more than 1? Okay. When relative is more than 1 means that the presence of exposure increases the positive outcome. Okay. The presence of exposure increases the positive outcome. But because, remember, this is binary. The risk exposure is binary. The outcome is also binary. Makes sense, right? So we are taking, let's say, heavy smoker. Then you have to define what is the cutoff criteria for heavy smoker. If heavy smoker increases the relative risk of, let's say, a lung disease at age 50 by 3 times, okay, then how about light smoker? So the exposure condition is different. Okay. On the other hand, when your relative risk is less than 1, what does that mean? Decreases, opposite way. The presence of exposure decreases the positive outcome. Okay. This will be in the example that, for example, let's say, exercise 3 to 4 times a week reduces chances of, let's say, your type 2 diabetes. Okay, so you expect the relative risk to be less than 1. Okay. Huh? No, it's not because of this. Okay, because D tends to be the largest, simply most people are not exposed to the risk, and most people do not have the outcome, especially in disease. Otherwise, you have, okay, D is usually the largest because B can also be one of the largest as well. B and D are actually supposed to be very big. Just most people do not have the disease, right, compared to people that have. Yep. With or without exposure. So the outcome, okay, and that also becomes another point. And where are we here? Okay. So if I were to reverse this, okay. Now it's a concept that you just raised up. Okay. By right, B plus D should always be much larger than A plus C. Makes sense, right? Since most people do not have the outcome. Okay. And most of the outcome that we are looking at is a disease state. Hopefully, less than half of the population have a disease, right? Otherwise, you'll be in big trouble for a lot of things. Make sense? So it also means that A and C is actually much smaller, the opposite way. Okay. So if relative risk is A over A plus B, C over C plus D, and we say that A is usually much smaller than B. C is usually much smaller than D in order for this to be true. Make sense? Therefore, can we, in the denominator, remove the A and C? Therefore, can we remove A and C in the denominators? Okay, so that becomes, okay, then this results in an equation that you have A over B divided by C over D. Makes sense, right? We are just removing A and C to be 0. Okay? Because really why? We are talking about A 0 plus B. C 0 plus D. So it becomes this equation. Okay? And this is what we call as the odds ratio. All right. So that's essentially how we come out for two different things. Yeah, you can definitely calculate them. But which one is more likely? Which one is more suitable? So that's why your lecture slides, the last page tells which one is more suitable. Okay, for cohort study or for your case control study. Yes. Cohort study, you can do both. Yeah. Odd ratio, then to be odd ratio. Okay. But this itself is okay, in reality, most papers that you are going to read, they will calculate both at the same time. Whether is it suitable or not suitable. Okay? Whether it's suitable or not suitable, they'll calculate both at the same time. Okay, just that we try to make a distinction. All right. Okay. Okay. So essentially, that's the main part that we have to cover today. And where is my? Okay. All right. Okay, so now let's go to our tutorial questions. Dustbin. Okay. So let's do tutorial question number 2. Tutorial question number 2 states that question 2. Okay. States that the probability of having a disease is 20%. Okay. But if a person has the disease, the test may not be 100%. Okay. So the probability of, so the probability of a positive test when the person has the disease is 90%. Okay, because not all tests are 100%. Okay, how about for those who do not have the disease? The person can still be having a positive result when this person is healthy, does not have the disease. The probability is 5%. Okay, so the problem, so let me just put it out in clearly first. This is basically the correct outcome, right? The chances of the correct outcome. This is technically the false positive. Make sense? You don't have a disease, but you're tested with a disease. That's called false positive. So what you want to calculate here is given the probability of the person actually have a disease when the test is positive. Correct? Because if a person have a disease, the test positive, right, doesn't mean that person is 100% having a disease because you have a positive, false positive. Make sense? So what is this value? This is also known as the positive predictive value of the test. Okay. So how do we do that? We set up with here, disease, no disease first. So what's the probability of having a disease? 0.2. No disease? 8. Okay. So positive, negative. So what is the probability of disease and positive? 0.9. The other one will be 0.1. So 10% of people is positive but tested negative. That's what I'm trying to say. And here you have positive and negative as well. Okay. No disease but you get positive is a false positive rate. So it's 0.05. The opposite is 95%. So what we want is the probability of disease given the positive test, which means that we want to take disease plus positive test over positive test. Okay. So how do we do it? Disease and positive test is very easy. It is actually this track, correct? So let me just color it first. This track we have 0.2 times 0.9. Okay, and positive, this is also positive, right? So it's still 0.2 times 0.9. Okay. However, we also have this positive as well. So we have to deal with this guy, okay, which is 0.8 times 0.05. So what is then the outcome? So let me see, 0.8, 0.82, correct. Okay, or 82%. Make sense? Now, does it appear interesting to you that the person is positive? That means the correct outcome, positive when having the disease is actually 90%, but when you test positive, the chance of a person actually having a disease is actually less than 90%. Okay, it's because of this set here. Make sense? So let us do something that's even more extreme. How about the disease and no disease becomes very extreme? Okay, can we do that? Just do save. Where are you? That's the one. Okay, so let's just say that. Okay. So we have a question. For example, the probability of the disease, in this case, the probability of disease in the environment, in the whole population. Let's say it is only 0.01%, or rather 1%. Okay, may be rare, maybe actually this is quite high already. Okay. But we also tell you that the probability of a positive test when the person has the disease is also very high, maybe 0.99%. What we want to find out now is what is the probability of having the disease given a positive test. Right? So then let's us draw the tree now. Okay. Disease, no disease. So here is 0.01. This is 0.99. Correct? Positive result, negative result, positive result, negative result. So positive result given a test is 0.99. Here is 0.01. Okay. 0.01 in the, okay, later. Here, oh, I forgot to tell you, but then there is also a false positive. So the probability of having a positive without the disease is also pretty low. Just keep it as 1%. Okay. Without disease is very low. So this is still 0.99, 0.01. Same numbers. Now, so let's work out the workout now. Yeah. Negative. Which one? 0.99 is supposed to be, yeah, correct. This works out right. Yes. 0. Okay. This is 0.99. This is 0.01. Okay. All right. Okay. So what we have is the probability. So let's reduce this. We want to calculate the probability of disease and positive test. Here is the probability of a positive test. So what is the probability of disease and positive test in this case? This one, correct? This track. Okay, so let's shade it out here first. So it's 0.01 times 0.99. This is also positive. So this is 0.01 times 0.99. Okay. Then the next thing is you have this track, right? Which is 0.99 times 0.01. So can you calculate out? 0.5. Yes. So even you have such a high probability, good, sufficient test, 99% is actually a very good test. You can be higher, but the maximum here is 100. It's never going to 100 anyway. Makes sense, right? You still only have half the chance of getting a disease when the first test is positive. Okay. Now we can actually pull this into more and more extreme cases. The reason why is that this is so low is because the probability of the disease is actually very low in the population. And no matter what, there is always false positive. Okay. So what we have is, let's look at this in itself. Have you all do clinical testing? Let's say you want to do tests, how do you actually read the results? Your clinical chemistry, have you done that? Okay. So in short, this is what it looks like. Having the disease and having a positive test This is what we call as the, oops, how come my pen is so fat? Having the disease and a positive test, this is what we call as the true positive. Okay. Having the disease but the test is negative, this is what we call as the false negative. Okay. Having no disease but the test is positive, this is actually the false positive. No disease and negative, this is a true negative. Okay. So this is actually quite important in our modern day society. Okay. For example, you know that HIV is a problematic disease, right? Okay, and the test is actually doing very well. But because the population having a disease is so low, the first positive, that means the ELISA test for HIV, if let's say you go for a HIV test and you get a first positive test, will you start crying? Try not to, because essentially the real positive is still 1 in 20 chance. Okay, you have to go for the second test, which is the Western blot test, to confirm. Okay, so if you both of them becomes positive as well, the chances of, that means there is still technically a chance of the overall false positive, right? Okay, so the overall false positive in this case, I calculated like 20 years ago, it is about 1 in 2 million. Which means that you can still have a tiny chance of being false, being wrong. Okay. So a lot of people will try to want to kill themselves at this point. Try not to. Okay. The first test is always a screening test. The second test is more a confirmation test. So in medical biology, there's always this type of two tests. Okay. This is why when your parents, especially your mom, go for a mammogram and all this stuff, the first thing is quite scary. Maybe you see that, okay, there may be the results comes out. If there's nothing will happen. Usually quite fine. Okay. Sometimes you ask to do a second test, and your parents will actually be, your mom will worry and start asking you questions. So you have to know how to pacify her. Okay. All right. Okay. 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 So now we have that. How about question number 3? What's your answer? 50%, correct. Question number 3 is 50%. Okay, those at home here, 50%. Okay. Okay, question number. Anyone want to show your answers? If you have your answers already, you can show. Anyone? Okay. So for question number 4. Okay, question number 4. Part 1. 54 divided by 79 is what fraction? Okay, let me just. So question number 4. Okay. Fraction 54 over 79 is what? Yeah, the overall rate. Okay, so this is a overall rate. So this is overall, this is a sickness rate of those attending the wedding. Okay. How about 50 over 54? Correct. Proportion Yeah, who say something? Who's squeal or something like that at home? Okay, proportion of illness by those that only ate or ate those ate the wedding cake. Okay, how about 50/53? Yes, the food specific attack, whichever that even means. Okay. So this is also quite important. How do you know that a food or a food store or anything is the cause of your diarrhea or your food poisoning? What is the standard at least? What is the minimum standard? For example, after you eat something, you go home next day, you have food poisoning, and then you want to complain. What is the minimum standard to complain? Yeah, correct. Minimum, you need 2 persons who ate the same thing and get the same problem. Okay, that's at least, right? Okay, okay, so what is the relative risk? Yeah, 6.13. So it's actually pretty high. That means you have 513% more chance of getting a, what do you call this? Yeah, food poisoning when you ate the cake. Okay. Okay. Question number 5. What is the relative risk and what is the odds ratio? Odds ratio is? Huh? What's the odds ratio? Anybody at home? Anybody at home want to say something? How about Rachel?
Sure. Can I ask about the question 4?
Okay, what about question 4?
The 50/54, right? I put food specific attack.
Food 50/54. Food
Yeah.
specific attack.
Yeah, because 54 people ate the wedding. Wait, 54 people got sick, but 50 people got sick because of the food.
So if you swap the proportion of patients eating the wedding cake, then that's wrong.
Can
Correct?
explain?
Okay, because the proportion of the people eating the wedding cake, you have more people eating the wedding cake. So you see, the proportion of the patients eating the wedding cake, there are a total of 54 people eating the wedding cake, but 50 are sick. Correct? Got what I'm trying to say?
The one that ate the wedding cake, isn't the total 53?
54.
But the total is on the right,
right,
at the
53,
top
53,
right.
53.
Yeah.
So 53 is the one that ate the wedding cake, correct? Okay, and because the people eat the wedding cake, they get sick. That's why it's called a food specific. How many of the people who ate the cake and get sick?
That's what food specific attack means.
No, then what does proportion of patients who ate the wedding cake means?
I don't know.
So because there are people who do not eat the wedding cake and still get sick. Yeah, I know this is a bit, the language is a bit problematic, yes. Just don't bother about this part first. Yeah, seriously, nobody will ask you that problem. Don't worry too much about that. Okay, yeah, and then this question has always been problematic, so just leave it first. the main thing is you calculate the odds ratio, relative risk correctly. Okay, so question 5, what's the relative risk? 1.70. 1.70. Huh? 1.69. Huh? Okay. How do you write? So you have, okay, your contingency table is this way. You have the death, no death, okay, and then the exposure is the medicine. That's the penformin. Huh? Smoking. Oh, okay. So that means
Yeah, our one is different question to yours.
for me, why they always like to do that? Okay. Okay. Question 7. Okay, so the performing one is which one? Question 7. Okay, so let's do question 7 first. Oops. Okay, question 7. Yeah. Yeah, so it's 0. This is 0.67 or 2/3. The other one? 0.615, correct. Where on earth is the smoking question here? Okay, so my question 6 is the study that found the smoking raises blood pressure. Why they change it? Okay, anyway. Okay, so the question 5 for you. Okay, high blood pressure. No, high blood pressure. Smoking, non-smoking. So what is the number here? 133. Yeah. 202. 167 and 548. Correct. Okay. 66666. Where is my, okay? So then what? In this case, what is the odds ratio? About 216. 2.16. Okay. All right. So the last one will be the chicken pox question. Right. Is that the last one? Okay, so what's question 8? Huh? Which means that I got the one that is the older version. Okay. Okay, so why not you, who has a question, you can show up. Okay. Okay, who has the question? Out of my hand finger. Anyone with the question? Let's see, I will unshare. Okay. And what do I do here? Yes. Come here. No, I will have to share my screen again. What am I doing? Okay, anybody with your laptop? You want to show your questions? What? Okay, so do you have AirTame? Okay, go and download it. Let's say online. Share your. Yes. So online people, share your screen. And for example, we have now who is this very muscular guy here? Anyway. Okay. Let's say, Lawrence, we want to share? Oh yeah, you cannot see correct. Hold on, how come this is, yeah, okay, hold on, share, okay, 8, 6, 7. Okay, Lawrence, share your screen. Actually, I'm not sure whether can it work this way, but let's try. Lawrence, are you there? Okay, Mr. Lawrence coming up. Okay. Okay, you realize that it's very tiny. Try to enlarge. Okay, so how do you calculate? Explain to us.
Wait, sorry. Explain the RR and OR.
Oh, read the question and explain to us how do you actually do it step by step.
Oh, okay. So there are basically two tables, and then they ask us which one is the correct and conventional contingency table.
Okay, so which one should be a correct contingency table?
I chose table 1. Yeah.
Table 1 is the correct one.
Okay.
Yep.
Do I need to explain why?
Table 1 is correct. Yep. Okay. Continue.
Then they ask us, is it a observational study or an experiment? I chose experiment.
Okay.
Is that correct?
Yeah. So how do you calculate the relative risk?
From table 1, I took 174 divided by 3302 here.
Yep.
And then divided by 248 divided by 3293.
Correct. Yeah, that's how you calculate relative risk. Okay.
Then, yeah.
So how do you explain your results?
I said the relative risk is less than 1, therefore it's less likely for the person that took the drug to die compared to the person who took a placebo.
Yes. Okay.
Then the next question is they say those who took the drug are less likely to die because it's between the relative risk is between 0.5799 and 0.8443.
Yep.
So yeah, it's.
So you have not covered confidence interval yet, okay? But if the confidence interval doesn't cover 1, in this case covers 1, that means it is not likely to be within the range. That means 1 is not likely within the range.
Yeah, it is not.
Okay. Yeah. Correct.
Okay. Then is the use of odds ratio a suitable measurement? I just put yes.
Use odds ratio as well. Yeah. Okay. All right. So any other questions? Yes. Okay, relative odds, which one you can use for everything? Relative risk is for everything. Odds ratio, you just cannot use for what study? Case control study. Because you do not know what is the original exposure. Correct. But as I say, this is a very blurry line. Because all the numbers are there. Correct? When you can calculate relative risk, you can calculate odds ratio. Makes sense, right? All the ABCD are there. So in reality, a lot of people don't even bother too much about it. They calculate both things at the same time. Yeah. What people what? I have no idea what's going to happen, you know. It could no. So So okay, when you draw, how do you draw a tree diagram on LMS, right? No, you can't. Yeah, just people, right?
Hello.
Yes,
Sure.
yes.
Just now you said, is it correct that you said that odds ratio? I thought odds ratio can find everything. Relative risk cannot find in a case control.
In case control, you can't. So what happened is, as I said,
Relative risk cannot find in case control, right?
yeah, correct.
Okay.
Okay. Now, actually, in the test, we do not bother whether you use paper to scribble your answers or not. Yeah, you have to. I mean, otherwise, how are you going to do your calculation? Yeah. Yeah. Because a lot of things this stupid lockdown browser is getting on my nerves anyway. Yeah, it is an irritating thing. To me, if you, as I always tell people, if you really want to cheat, a lockdown browser is not going to help you not to cheat. You can bypass a lockdown browser very easily. You know? Yes, you can kind of go out. Yeah, I even tell the people in the school, I have three laptops and 4 tablets at home. How many you want to lock down? Yeah, now I'm seeing exactly what you're seeing, right? So that I know what's happening. Yeah. In fact, your own system, there's a way to escape lockdown browser as well if you know how to do it properly. No, I'm not telling you how to cheat, but lockdown browser is, to me, lockdown browser is the point of you are trying to prevent as much as you can. But lockdown browser structurally only works at best if that person has only access to one computer at a time, which half of the household, that doesn't even apply, right? You know? So sadly, lockdown browser is disadvantaging the less privileged people that have only one computer share around the whole house. Okay. Yep. So that's all. In fact, huh? Oh yeah, question 1. Yes, question 1. Okay, question 1. Consider a random sample of 100 female students and 100 male students from TP. Suppose 5 female use handphone and 62 males use iPhone. What am I talking? What is the estimated difference in proportion? Is 0.07. True or not? What question 1? Okay, can somebody help me on those who are online? Help me flash up question 1 so that the rest can see. Grace, will you mind? What's the answer?
My answer for which question, sorry?
Just share your screen and show us question 1. The text for question 1.
Okay.
Okay. Yes, so question 1, is it true or false? Can you expand out? Yeah, zoom in. It's a bit hard to see as well. Okay, yeah, correct. Okay, so question 1, true, false? Yeah, of course. Somebody? It's actually true. Because it's a difference in proportion. Difference is just minus, ma. Yeah, correct. Okay. Okay. Question 2, we always have the option to use relative risk. It is false because 2 category variable. Yeah, question 2 is false. Okay. Question 3, Working as a barrister and being a TP student are mutually exclusive events. That means you cannot be a TP student and work as a barrister at the same time. Is that true or false? False, because you can do part-time work, right? Yeah. So C is also false. Okay, if I sample without replacement, the future probabilities are unaffected. Without replacement, that means you take, let's say in a basket of balls, you take one, you don't put it back. False, because you already removed the numbers. Okay. 5, for intervention that has a greater chance of event, the odds ratio will be larger than relative risk. True. Okay. And you will always find the odds ratio tends to be larger, it's always larger than relative risk. Okay, because you divide the denominator by a smaller number. Okay. Which one? A and B. Question 1, because you are looking at the difference in proportion. So how many percent lesser? That's for question 1. Okay. Question 2 is you always have the option to use relative risk and odds ratio to measure 2 category variables. This only applies if you technically you can say that you can use relative risk and odds ratio for both cohort and case control studies. Yeah. So yes, you'll find that the true-false question for all the tutorials is very language-based. Yeah. Huh? I try not to. Actually, I don't see a question at all. I am not invigilating your class. I'm invigilating M2, but I'm not the one setting a question, so I don't know. Okay. Any problem? Okay, so basically no problem. Then that's all. I will upload I'll upload the what am I saying? Upload the video when I have time. Okay, bye bye. You can go off now. Yes, online tutorial are faster. Okay.
Thank you. Bye bye.
Bye bye.
Bye-bye.